Welcome to this presentation. In this presentation, let us have an insight of magnetic resonance imaging. Nuclear magnetic resonance tomography has emerged as a powerful imaging technique in the medical field because of its high resolution capability and potential for chemical specific imaging. Although similar to X-ray computerized tomography, that is CT, it uses magnetic fields and radio frequency signals to obtain anatomical information about the human body as cross-sectional images in any desired direction and can easily discriminate between healthy and diseased tissue. NMR images are essentially a map of the distribution density of hydrogen nuclei and parameters reflecting their motion in cellular water and liquids. The total avoidance of ionizing radiation, its lack of known hazards, and the penetration of bone and air without attention make it a particularly attractive non-invasive imaging technique. CT provides details about the bone and tissue structure of an organ, whereas NMR highlights the liquid-like areas on those organs and can also be used to detect the flowing fluids like blood. A conventional X-ray scanner can produce an image only at right angles to the axis of the body, whereas the NMR scanner can produce any desired cross-section, which offers a distinct advantage to and is a big boon to the radiologist. So MRI is the radiology technique which uses magnetism, radio waves and a computer to produce images of body structures. MRI is based on the principle of NMR. In 1997, the first NMR was performed on a human being. It took 5 hours to produce an image. This diagram shows the practical structure of NMR system. And the main advantages of NMR are it has no ionizing radiation and it has variable thickness in any plane and it has better contrast resolution. It can provide many details without IV contrast. And the disadvantages of NMR or MRI is it is highly expensive and it is dangerous for patients with metallic devices placed within the body like a pacemaker, and it is difficult to be performed on claustrophobic patients, and movement during scanning may cause blurry images. RF transmitters can cause severe burns if mishandled. Now let us see the biological effects of MRI. The three aspects of NMR imaging which could cause potential health hazard are heating due to RF power. The temperature increase produced in the head of the NMR imaging would be about 0.3 degrees Celsius. This doesn't seem likely to pose a problem. And although no significant effects of the static field with the level used in the NMR are known, the possible side effects of electromagnetic fields. So next one is electric current induction due to rapid change in magnetic field. That is, it is believed that oscillating magnetic field gradients may induce electric current strong enough to cause ventricular fibrillation. So these are the biological effects. And MRI scan can be diagnosed by for particular people like most ailments of the brain and including tumors, sport injuries, musculoskeletal problems, most spinal conditions and injuries, and vascular abnormalities, and female pelvic problems, prostate problems, and some gastrointestinal tract conditions, certain ear, nose, throat, ENT conditions, soft tissue and bone pathology conditions. Now let us have a look into the principle of NMR system. MRI makes use of the magnetic properties of certain atomic nuclei. Hydrogen nucleus present in water molecules and therefore in all body tissues, and the hydrogen nuclei partially aligned by a strong magnetic field in the scan. The nuclei can be rotated using radio waves and they subsequently oscillate in the magnetic field while returning to equilibrium. Simultaneously, they emit a radio signal. This is detected using antennas. Very detailed images can be made of soft images. This diagram shows the arrangement of hydrogen atoms without a magnetic field and with magnetic field. When the magnetic field are applied they are aligned in a particular direction. They are oriented in the same direction. Right. Now let us see the basic NMR components. It consists of a magnet which provides a strong, uniform, steady magnetic field B naught, and an RF transmitter which delivers radio frequency magnetic field to the sample. A gradient system which produces time varying magnetic fields of the controlled spatial non-uniformity, a detection system which yields the output signal, and an imager system including the computer which reconstructs and displays the images. The imaging sequence in the system is provided by a computer. This is the block diagram of the typical NMR imaging system. So functions such as gates and envelopes for the NMR pulses and blanking for the preamplifier and RF amplifier and voltage waveforms for the gradient magnetic fields are all under software control. The computer also performs various data processing tasks like including the Fourier transformation, image reconstruction, data filtering, image display and storage. Therefore, the computer must have sufficient memory and speed to handle large image arrays and data processing in addition to interfacing facilities. And now let us see about the magnet. In magnetic resonance tomography, the base field must be extremely uniform in space and constant in time, as its purpose is to align the nuclear magnets parallel to each other in the volume to be examined. So also the signal to noise ratio increases approximately linearly with the magnetic field strength of the basic field. Therefore, it must be as large as possible. 4 factors characterize the performance of magnets used in the MR system, like field strength, temporal stability, homogeneity and bore size. The effect of the magnetic field strength has been elaborated, and the temporal stability is important since instabilities of the field adversely affect resolution. The gross non-homogeneities result in image distortion, while the bore diameter limits the size of the dimension of the specimen that can be imaged. Such a magnetic field can be produced by means of 4 different ways, like permanent magnets, electromagnets, resistive magnets and superconductor magnets. So the magnet is the most expensive part of the whole scanner, and in case of the permanent magnet, the patient is placed in the gap between the pair of permanently magnetized pole faces. Permanent magnet materials normally used in MRI scanners include high carbon ion alloys such as alnico iron and ceramics such as barium ferrite. Although permanent magnets have the advantage of producing a relatively small fringing field, do not require power supplies, and they tend to be very heavy and produce relatively low fields of the order of 0.3 Teslas. Now, and the next category is electromagnets. They make use of magnetic materials such as pole faces, which become magnetized only when electric current is passed through the coils wound around them. Electromagnets obviously require external electrical supply. So on cost considerations, the earlier NMR imaging system were equipped with resistive magnets. Resistive magnets make use of large current carrying coils of aluminum strips or copper tubes. In these magnets, the electrical power requirement increases proportionally to the square of the field of strength, and which becomes prohibitively high as the field strength increases. Moreover, the total power in the coils is converted into heat, which must be dissipated by liquid cooling. So for instance, at 0.3 Teslas, the power requirement is nearly 70 kilowatts, and a substantial increase of the field strength about 0.2 Teslas in resistive magnets is thus technically limited. At present, resistive magnets are seldom used except for the very low field strength applications, generally limited to 0.02 to 0.06 Teslas. So most of the modern NMR machines utilize superconductive magnets. These magnets utilize the property of certain materials which lose their electrical resistance fully below a specific temperature. The commonly used superconducting material is niobium titanium alloy, in which the transition temperature lies at 9 Kelvin. In order to prevent superconductivity from being destroyed by external magnetic field or the current passing through the conductors, these conductors must be cooled down to temperature significantly below this point, at least to half of the transition temperature. Therefore, superconducting magnet coils are cooled with liquid helium, which boils at the temperature of 4.2 Kelvin. The helium container with its superconductive windings is enclosed in a vacuum to keep the evaporation rate low. Internal shields cooled with liquid nitrogen prevent heating due to radiated heat passing through the vacuum vessel. So in the superconducting magnet, connection to a current supply is only necessary for energizing up to the required field strength. After this, the coils are short circuited and require no further electric energy. The magnetic field is temporarily stable. So in the case of supermagnet. Okay, the fields from such magnets are very stable with time, which is essential for an MRI system. And the next case is gradient coils. The requirement of gradient coils are twofold. First, they are required to produce a linear variation in the field along one direction, and secondly to have high efficiency, low inductance and low resistance. In order to minimize the current requirements and heat deposition, linear variation in field along the direction of the field is usually produced by the Maxwell coil. This consists of a pair of coils separated by 1.73 times greater than their radius. Current flows in opposite sense in the two coils, which produces a very linear gradient. When the MRI system is in resting state and not actually producing an image, the magnetic field is quite uniform or homogeneous over the region of the patient's body. However, during the imaging process, the field must be distorted with gradients. A gradient is just a change in the field strength from one point to another in the patient's body. The gradients are produced by a set of gradient coils which are contained within the magnet assembly. During an imaging procedure, the gradients are turned on and off at many times, and this action produces the sound and noise that comes from the magnet. So this diagram shows the variation of the field along the distance. So in the top figure, you can see that the gradient increases linearly with the distance. Whereas without magnetic field or without gradient coils off, the field strength is uniform throughout the distance. And next, let us consider the RF transmitter system. In order to achieve the nucleus so that they emit a useful signal, energy must be transmitted into the sample. This is what the transmitter does, and the system consists of an RF transmitter, RF power amplifier and RF transmitting coil. The RF transmitter consists of an RF crystal oscillator at normal frequency. The RF voltage is gated with the pulse envelopes from the computer interface to generate the RF pulses that excite the resonance. So these pulses are amplified to levels varying from 100 watts to several kilowatts depending on the imaging method and are fed to the transmitter coil. The high power levels are necessary for the large sample values encountered in the whole body experiments. The RF coil can either be a small single coil serving as both transmitter and receiver, or two separate coils that are electrically orthogonal. The later configuration has the advantage of reduced pulse breakthrough into the receiver during the pulse. In both cases, all coils generate RF fields orthogonal to the direction of the main magnetic field, and the coils are turned to the NMR frequency and are usually isolated from the remainder of the system by enclosure in an RF shielding case. So for magnetic fields in the range of 0.05 to 2 Teslas used for imaging of the human body, the resonant frequencies fall in the radio frequency band. For example, in the field of 1 Teslas, H resonates at 42.57 MHz and F at 40.05 MHz and P at 17.24 MHz. Usually the resonance is extremely short, which in the range of 10 Hz are typical biological system. And the next case is the receiver. A short time after a sequence of RF pulses is transmitted to the patient's body, and the resonating tissue will respond by returning an RF signal. These signals are picked up by the coils and processed by the receiver. The signals are converted into a digital form and transferred to the computer when they are temporarily stored. These pulses are amplified to levels varying from 100 watts to several kilowatts depending on the imaging method and are fed to the transmitter coil. The RF coil can be either a single coil serving as both transmitter and receiver, or two separate coils that are electrically orthogonal. In both cases, all coils generate RF fields orthogonal to the direction of the magnetic field. And the next case is the detection system. The function of the detection system is to detect the nuclear magnetization and generate an output signal for processing the computer. And the receiver coil usually surrounds the sample and acts as antenna to pick up the fluctuating nuclear magnetization of the sample and converts it into a fluctuating output voltage. The receiver coil design and placement is such that B of X has the largest possible transverse component. The longitudinal component of B of x contributes little to the output voltage and can be ignored. The RF signal constitute a variable measured in magnetic resonance tomography. These are extremely weak signals having an amplitude in the nanovolt range and thus requires specially designed RF antennas. The sensitivity of the MR scanners therefore depends on the quality of its RF receiving antenna. For a given sample magnetization, static magnetic field strength and sample volume, the signal to noise ratio of the RF signal at the receiver depends on the SNR ratio, that is SNR is equal to K into Q by Vc, where K is the numeric constant, Q is the coil magnetization factor and Vc is the coil volume. And the pre-amplifier is a low noise amplifier which amplifies the signal and feeds it into a quadrature phase detector. The detector accepts the RF NMR signals, which consist of distribution of frequencies centered around or near the transmitted frequency omega, and shifts the signals down in the frequency by omega. The detector circuit accepts the input, the NMR signal V of t and a reference signal, and multiplies them so that the output is the product of two inputs. The output of the phase sensitive detector and consists of the sum of the two components, one a narrow range of frequencies centered at 2 omega naught and the other a narrow range centered at 0. The low pass filter following the phase sensitive detector removes all components except those centered at 0 from the signal. It is necessary to convert the complex signal to two strings of digital numbers by analog to digital converters. The A to D converter output is passed in serial data form to the computer for processing. The detector circuit accepts the inputs and the NMR signal V of t and the reference signals and multiplies them. The frequency of the reference signal is the same as that of the radiating RF pulse. Thank you.